This conference will now be recorded.
Starting from specification till we manufacture the chip, it goes through various stages. It is divided into two parts majorly. One is the front end domain, one is the back end. So it is not possible for us to do one demo session for architecture, one for design, one for integration. Separately, it's not possible. So we will have to conduct almost 12 to 15 demo sessions just for each and every domain. Rather, what we do is we have one common demo session for entire front end domain. Then those who are interested, some of you would be interested in FPGA training, right? For them specifically, we'll have one more demo. People from DFT again will have one more demo session. Specific to the people who are looking for individual topics, there will be a demo. Now, today's demo session will be like those who are looking for functional verification, that is RTL design verification or Verilog system Verilog kind of training. This would be a complete demo for them. Okay. I hope you understood the intent behind having a common demo so that initial part of the demo will be common to everyone, like where we give the course overview, how the sessions will be conducted, everything. Then we'll be having dedicated demo for these topics. Our admin will inform you what will be the schedule for design integration, what will be the schedule for DFT, what will be the schedule for FPGA training. Uh, so let's quickly start off the agenda. Basically, today's demo, as I said, it's for RTL design and functional verification. Like sometimes we may call the same course as functional verification training. The same course is called as front-end training for freshers. Same is called as ASIC verification. Everything refers to the same thing. Other than that, we are also starting today's demo is for functional verification training for experienced engineers. So, what is the significance of this? Is if you talk from a fresher perspective, the fresher generally would not be familiar with the digital design in depth, Linux, Verilog, even some scripting. They won't be familiar. Whereas when we come to experienced people, they are already working in the industry, they want to learn the advanced aspects. So that is where their training directly starts with system Verilog. I mean, they won't have the digital design and Verilog. So, but irrespective of that, today's demo session is meant for those people as well. Next. Other than that, we also today's demo is also for people who want to join Verilog for design and verification, who want to join for system Verilog course also. And again, for people who are looking for FPGA design and verification, RTL design integration, DFT. So these are all the courses for which this demo session is there. As I said some time back, for the people who are looking specifically for these domains, we have the list of people who are looking for these domains, right? Like when you have filled the registration form, accordingly, we'll intimate you what is the exact schedule for these specific domain sessions. I will be talking about each of them briefly, like what is FPGA, what is DFT, what is RTL design integration, and I will also be giving you inputs on which course, how to choose the right course. Uh, about myself, I have close to 15 years of experience. Uh, I mean, I have been teaching since 2012. 2019, I have quit my job and full time into training since then. Uh, Now, talking about the courses that are offered, uh, one second, give me. Actually, there are multiple copies, so I just took a wrong copy. Uh, So you might have seen this demo video on our YouTube channel, but I would still go over this. What is the purpose of today's demo session is not to teach functional verification, not to teach FPGA. It is to give you an overview of what all domains you can explore after your BTech. Let's say if you are interested in electronics domain, you can explore VLSI, you can explore embedded system. Even in VLSI, there are two domains, ASIC domain, FPGA domain. And on the other side, you can explore embedded system. I'm just going to give you a brief about each of these domains, and based on that, you will be able to make a better decision. So let's start off with understanding an electronic system. Let's take an example of a mobile phone. So when we say mobile phone, what goes into a mobile phone? Can someone tell me? You would say the various elements like antenna, modem, the PCB board itself, and the processor, the USB, various things put together is what makes the mobile hardware, right? So what all things makes up? First thing is the chips, processors, the screen you see, and the USB port, camera, sensors, and audio speaker. These all things makes up the hardware part of the electronic system. But is this sufficient for mobile phone to work? Just having chips and processors and everything, will it be sufficient for it to work? No, right? It won't be sufficient, because it is just a it requires, there are things which we don't see. For example, the operating system. Without operating system, the mobile phone cannot function. Then firmware is something we don't see, and the applications. So majorly putting together all these things, the hardware, the operating system, the firmware, and applications is what collectively makes the electronic system. So in summary, mobile phone has four layers. It can be mobile phone or any electronic system. First thing is the hardware layer. What is there in the hardware layer? Processors, camera, sensors, various other things. Who develops the hardware? What is that person called as? The person who develops the hardware is called as the VLSI engineer. Now, this VLSI engineer could be the functional verification engineer, it could be the physical design engineer, it could be DFT engineer, it could be integration engineer. You take any person in the VLSI flow, we will call him as VLSI engineer. Then comes the subdivision. Then what is the next layer after the hardware? We have firmware, also called as drivers. When you have studied, if you have listened to, I mean, if you have exposure to the basic embedded systems, you would have heard terms like drivers, USB drivers, right? Something like that, right? So those drivers, who develops the firmware? Firmware is developed by embedded system engineers. So you need to understand the primary difference between VLSI engineer, embedded system. So what does VLSI engineer is responsible for? He is responsible for manufacturing of the hardware. Okay. It's not one person who manufactures the mobile phone. Let's say if I take an example of a house construction, is it only done by one person? No, right? There are almost 50 people or 10 stages involved, starting from the architect, then the contractor, Mestri, then you have the plumber, painter, various people put together makes the house construction, right? All those people are called as, they are all involved in the construction activity. Collectively, same way, to make a hardware, various people are involved. They are collectively called as VLSI engineers. Then once the hardware is developed, between hardware and the operating system. See, what is the operating system most of the mobiles? Android, right, or iOS. Between Android and the hardware, there is one more layer which again you don't see. We cannot see that because we never open the phone, and that is something code which we cannot see. What we see is only the physical entity that is visible to us. So there is something which is present between hardware and the operating system. They are called as drivers. Who develops the firmware? It is embedded system. Let me give you an example of a driver. When you connect, let's take an example of a laptop. You connect a pen drive. What happens? It will immediately tell you that Western Digital 1 terabyte hard disk is connected, or some music player is connected, or some printer is connected. It will exactly tell you. HP printer is connected. It will tell you. So how is it detecting? How my laptop is detecting that this is connected? I mean, what is the type of device? That is the role of the firmware. So firmware which is present in my, where do you think firmware will be present? Will it be present in my laptop or will it be present in the pen drive? Actually, it will be present in both of them. Okay. Majorly the one which is doing this work is the firmware that is present in my laptop initiates some transactions to the pen drive to get the information. There will be something called as registers which are present in my pen drive. It gets that information. When it gets that information, it gets to know that this is from Western Digital. The hard disk capacity is 1 terabyte. It is a storage device, or it is a music player, it is a printer. It will get to know all the information. So who is doing all that work? It is done by the firmware. Then what is the next layer on top of firmware? Operating system. So what is the operating system example? Android OS, iOS, Windows, Linux. These are all the examples of the operating system. Who develops the operating system? They are in general called as software engineers, right? They're in general called as software engineer. You go to Google, someone who is working on the Android OS, you will call him software engineer. On top of operating system, what do you have? Applications. You know, right? Apps, Play Store, iOS apps, right? Uh, Apps in the mobile phone. It could be GPay, Maps, various applications, right? WhatsApp, all those things. Who develops the application? Again, they are also called as software engineers only, or application developers, right? Why this? Why we are trying to understand this hierarchy? It is to understand as a VLSI engineer, where do we stand in this flow in the electronic system? What is our role? Our role is to develop the hardware, basically. Okay. Then, do you understand the role of a firmware? Why is it the term driver is called, I mean, why is it called as driver? Because it decides how the hardware should function. Let's take a simple analogy. A bus driver. So the bus is like the hardware. Bus is like the hardware. The bus driver is the person who is deciding how the bus should move, when to stop, when to go. And does he do the decision independently? Does he decide everything? No. Sometimes he gets the instructions from application layer. Sometimes he gets the instructions from operating system. There he decides that how the hardware should be controlled. That is the same case in bus also, right? Let's say sometimes the bus driver may get a call from his authority, higher authority, that now stop the bus, now move the bus. Okay, now increase the speed of the bus. You need to reach quickly, so increase the speed of the bus. Everything he decides either through his pre-programmed instructions, whatever instructions we have given to him, or the instructions he gets from the upper layers. So in summary, this should have been reverse actually. This should have been the topmost layer. Applications are the top of the system. The applications will interact with operating system. Operating system interacts with firmware. Firmware finally interacts with hardware. This much brief is sufficient. So now going to the VLS engineer, we need to understand the in depth of how processor work, how this hardware works, how they interface with each other. Coming to the firmware, they need to understand how to give instructions to the hardware to make sure that it works. Like bus driver, he don't need to know. Bus driver don't need to know how engine is manufactured, how the steering is manufactured. He only need to know how to control the bus, right? Do you understand the primary difference? So the one VLS engineer is like the person who manufactures the bus. Okay. Firmware engineer is like the bus driver who understands how to use the bus effectively, how to drive it, how to stop, how to increase the speed, various aspects of it. So that is the difference between VLS engineer and embedded system engineer. Why I'm emphasizing this is sometimes people tend to have a confusion between what is VLSI and what is embedded system. And there are people who sometimes think that both of them are same. They are not same. Okay. Now, if you're talking about VLSI, it's a big domain. We can correlate it very similar to a house construction. Let's say you want to construct a house. Does it get over immediately? No, right? It doesn't get over immediately. How much time it will take? Is there any definite answer how much time it will take? No. Why? Because you will ask me, what is the type of house? How big is it? Let's say I only want to construct one room. We can get it done in 15 days. You want to construct a big bungalow, it will take at least 1 to 2 years. So, same way, if you want to manufacture a hardware, there is nothing like we can manufacture it in 1 week or 1 year or anything. It depends upon what is the complexity of the hardware we are manufacturing. But irrespective of that, whether you construct a room, whether you construct a big bungalow, doesn't matter. Almost all the people are involved. Sometimes you don't need architect. Let's say I want to construct a single room. Will I go to architect? No, right? I will make some of my decisions myself. But then you need other people like painter, the masonry, the plumber, whatever, right? So that is the difference between various hardwares. They all go through the same common process. So that is something we have listed here. Okay. So before we go into the hardware, so you understand what is VLSI, right? VLSI stands for very large scale integration. So what are we trying to integrate? Let's say if I'm constructing a house, what am I trying to integrate to make a house? I'm integrating the bricks. I'm putting together all bricks to bring it to a specific shape. What if I place all the bricks in one place? What will happen? Will it become a house? No, right? So here also in VLSI also we are trying to integrate something. In case of house, we were integrating the bricks. Now, if the house is very big, lakhs of bricks. If house is small, thousands of bricks. So the difference is only that much. In VLSI, what are we trying to integrate? Transistors, basically. What are the different types of transistors? BJT, MOSFET. Then you have got the PMOS, NMOS. Then you have CMOS. Then we have FinFET. Okay. So why we need so many types of transistors? Can someone tell me? This is the initial thing they started off with. Later they figured that this is a what type of device is it? Current control device. Current control device, and it is not efficient. Then they moved to field effect, voltage controlled transistors. All these things, MOSFET, CMOS, FinFET are all what? Voltage controlled transistors, right? Then they figured that MOSFET has what? The signal integrity issues. What are the issues? Due to the second order effect, what we call as short channel effects. So I'm not going to teach you what is short channel effect and everything. I'm just what we are trying to understand is how we moved from BJT to CMOS, from CMOS to FinFET. Now, if I take my mobile phone, what is the transistor that is present in my mobile phone? it will be FinFET. So that there is some order is there, like anything below 22 nanometer is always FinFET. Above 22 nanometer, it can be CMOS also, MOSFET also. And there will be a cutoff for BJT also. So going back to VLSI, very large scale integration. So what are we integrating? We are integrating transistors. There are two major styles of developing the chips. Like whatever, there is a chip that went into this mobile phone. These chips can be manufactured in two major styles. One is called as ASIC, one is called as FPGA. There are two major styles. One is ASIC, one is FPGA. Let us try to understand the difference between ASIC and FPGA. ASIC stands for application specific integrated circuit. So what do we mean by application specific? A hardware developed specific for specific application. Let's say mobile phone. Can we use mobile phone chip as a router? Let's say I will take out this mobile, I mean whatever chip that is present in my mobile phone. Can I use it as a router? No, right? It cannot be used because the person who has developed this mobile phone, he has developed it specifically to behave like a mobile phone only. Again, can I use the same chip like a laptop chip? Both of them have similar features, right? I can open the applications, I can run the applications, I can send messages, all those things. Even laptop has something similar to that. I can open the mail, I can send the mails. But can I use the chip that is developed for mobile phone application as a laptop hardware? Can I use it? It is not possible, right? It is because the chip was developed specific for specific application. So in now coming to the other one, what is other domain? FPGA. What does FPGA stand for? Field Programmable Gate Array. Field Programmable Gate Array. It is the same hardware, can be programmed to behave like different applications. Now, when it comes to FPGA, I can take the same hardware, I can configure it to behave like a mobile phone chip. I can configure it to behave like a laptop hardware. I can configure it to behave like a router also. That means what? In case of FPGA, if I take one FPGA board, high-end board, I can make it behave like a mobile phone. Same thing can be configured to behave like a laptop chip. Same thing can be configured to behave like some other router. Which one is better? ASIC is better or FPGA is better? FPGA looks very good, right? Because you are able to take the same piece of hardware and you are able to use it like different hardwares. But as you learn more deep into ASIC and FPGA, you will understand that ASIC is more preferred. Even though FPGA has an advantage. What is the advantage? The same gate array. What is FPGA? The gate array is programmed. See, it is programmable to behave like a different applications. You have a gate array. What is mean by gate? What is the gate we are talking about? When we say gate array, what is the gates we are talking about? Standard cells. AND gate, OR gate, multiplexer, XOR gate. So what is FPGA is? It's like a big board which has got array of gates. Here there is a gate. Here there is a gate. Here there is a gate. Now that gate is very generic. You can program it. You can program it to behave like a AND gate. You can program it to behave like a OR gate, NAND gate, NOR gate. Because of that, since you can program any point to behave like anything, any point in this, see, this is generally called as array, right? Two-dimensional array, generally we call it as. So in this array, Every point represents one gate, assume. That point can be programmed. That is why we are using the term program. You can program it to behave like a AND gate, OR gate, NAND gate, NOR gate, XOR gate, XNOR gate, whatever gate you want. Because of that, you can take the same piece of hardware and get whatever behavior you want out of it. It's not so straightforward. I mean, the FPGA boards are more and more complex than what you might be knowing. Like you may be knowing Spartan boards, things, right? But FPGA boards are even more complex than what you might be knowing. Okay, but let's just only keep it at a very basic level. So now, do you understand what is meant by field programmable? This is like a field. This red box, what I have drawn, is like a field. On that, you are able to program, and you get the required behavior out of it. Because of that, this same piece of hardware can behave like a mobile phone, can behave like a laptop chip, can behave like a router. Whereas in case of ASIC, they manufacture. At the time of manufacturing itself, they decide that this will be AND gate, this will be OR gate. You cannot change it. You cannot change OR gate to NAND gate, NAND gate to NOR. You cannot change it. Because of that, once you have manufactured this as an ASIC, it is fixed. It will behave like only like a mobile phone. Now, from this point, it looks like FPGA is better because it provides me flexibility to use it the way I want. But as you study, as we see in the next couple of slides, ASIC is more cost effective. ASIC is more cost effective. That's why companies prefer ASIC based production. Okay, that hardware is called as FPGA board. FPGA board can be programmed to behave like a mobile phone, can be programmed to behave like a laptop chip, whatever you want. Let us try to understand the difference between ASIC and FPGA. First thing we have already understood how the flow differs. In case of ASIC, when I start from the day one, I will develop with the intention that it need to be used for specific application. In case of FPGA, they don't have anything. They have a generic board which can be configured for whatever behavior we want. Let us understand what is the cost of ASIC design flow. Basically, it requires multi-million dollars since we need to start everything from the scratch. The flow of ASIC, basically, once flow is working, per chip cost will be less. Whereas cost of FPGA is few thousands of dollars or less. Hardware is already available. In case of ASIC, you don't have anything. You have to manufacture the hardware. Whereas in case of FPGA, hardware is already available. You just have to purchase the hardware and you will also get the applications. Let's say you are purchasing Xilinx FPGA board. You are all familiar with Xilinx, right? Because during your BTech, any VLSI course, you would have touched FPGA boards. Why you have done that? Because it only costs few thousand, very less amount. I mean, hundreds of dollars or less than that also to buy a FPGA board. So once the hardware is available, you just need to implement your logic onto the hardware. Per chip cost will be more. So in summary, how it works is basic flow. Implementing the flow takes, let's say, $1 lakh. Just an example. Implementing the flow means what? Coming up with the design, then developing the code, verifying that that code is working fine. So what do you mean by implementing the flow? This whole thing. Starting from coming up with specification, defining the behavior, then developing the Verilog code, then verifying the code, whether it's working fine or not. then going through the synthesis, physical design, various stages. Let's say it takes $1 lakh, for example. Generally, all these things are calculated in the dollars, so I'm taking dollar example. Okay. Uh, once you have implemented the flow, what is the output of this stage? Output of this stage is called as GDS2 file. What is the output of the VLSI flow? Let's say for me, the output of my construction is what? House, the readily available house. In case of VLSI flow, you're going through all this flow. Finally, you get one file. What is that file? GDS2 file. I'll give you a simple analogy. Let's say someone is making a movie, right? And they want to give you the file. So they have gone through various stages, right? Editing, shooting, everything. We have gone through various stages. What is the final format of the file? It could be MP4 file. They will give you one MP4 file which you will play in your video player and you will be able to watch the movie. Same way, when I have to manufacture a chip, I need to give one information, right? I need to give information to the foundry. So what is a foundry? A place where the chips are manufactured. Which are the some of the examples of foundries? TSMC. Okay, I think SMC or something is there, right? There are almost 10 foundries are there, but 3, 4 are major foundries. Okay. What is that? Let's say I go to TSMC and I tell them that I want some of the chips to be manufactured. What is that they are going to ask me? They are going to ask me this file. Give me the GDS2 file. So this file when I give, they will manufacture chip in a like a plate form. Each part of the plate, let's say if I cut it like this will represent one chip. This is one chip. So chips are kept in the array format. This one is what goes into my mobile. So coming to ASIC, this per chip cost will be very less. Let's say, for example, TSMC charges me $1,000 or let's say $5,000 for example for one plate. Okay. And each plate can have 200 chips. So per chip cost will be how much? $5,000 by 200. It will come to $25. So the per chip cost will be $25. This is based on ASIC. Coming to FPGA flow, FPGA board itself, FPGA board costs, let's say, $100. The same logic. Thing is, you don't have much initial investment. Initial investment is less, but running cost will be higher. What do you mean by running cost? Once you come up with the flow, each FPGA board is going to cost you $100. Whereas in ASIC, once you have implemented the flow, per chip cost will be lesser. You understood the difference? You may ask why this will be costlier. Because they have to create a very generic FPGA boards. See, these FPGA boards are very generic. They are not specific to any application. They are not specific to a mobile phone. They are not specific to laptop, or they are not specific to router. Because of that, their cost will be more. This $100 is just a rough number. Okay, don't take literally. That you will see FPGA boards which are thousands of dollars also. FPGA boards which are hundreds of dollars also. But coming to ASIC, it is 25 years. Now let us come up with a cutoff number where till which point ASIC FPGA is more productive. Till which point FPGA is productive, cost effective. Let's say I'm manufacturing n chips, n number of chips. So what is the ASIC cost? plus 25, right? 1 lakh is what? Fixed cost. In ASIC, even if you manufacture only one chip, okay, let's say you go to Qualcomm, they are manufacturing only one chip only. They still have to incur this one lakh dollars. They still have to incur $1 lakh. Whereas let's say they same thing they are implementing using FPGA, for example. They don't have that $1 lakh expense. Mostly expense will be less. They just have to use the FPGA board, which is already available, whose cost will be $100. Are you getting the point? The initial cost of ASIC will be higher because you have to go through a very costly process. The cost is mostly due to EDA tool license and number of engineers involved. Why the cost ASIC flow? I mean, you may say, why won't that cost be there in FPGA? It will be there, but the tool licensing will be lesser because when you go to Xilinx, they themselves provide the software tool. You might have seen Xilinx ISC, right? So the Vivado, various software they provide, you can use already. The number of engineers involved will also be lesser compared to ASIC. Number of engineers involved will also be lesser because of that. Whereas in FPGA, let's say the initial investment is less. Let's assume that this happens to be $10,000. So this will come to per chip cost is how much? 100. So you have to find this number. So basically, it will come to plus 25n equal to 100n. So it is comes to 75n equal to 90,000. So n comes to roughly 1200 chips. Means anything up to 1200 chips, FPGA is cost effective. Let's say, what is 1200 chips? It is the number of chips that everyone collectively using. Let's say I'm using one mobile phone. Am I the only person who is using this mobile phone? No, right? There could be lakhs of people who are using this kind of hardware. Even if it is, let's say this is MI phone, MI brand, okay. Even if you take one more brand called as, let's say, OnePlus, it is highly possible that in OnePlus and in MI, same hardware is going. In MI also and in OnePlus also, the same hardware. It could be the Qualcomm which manufactures the hardware. The Qualcomm will manufacture in bulk. They will sell 5 lakh chips to OnePlus. They will sell 5 lakh chips to MI. They will do their own packaging and release it to you. Because of that, when you take a mobile phone, how many chips do you think mobile phone manufacturers would be doing? Lakhs, right? So it is much more than 100 chips in this case. So which one do you think will they use? Let's take laptop hardware, the one which you are using, right? Is it only used in specific places, or does everyone use laptop? Almost everyone uses laptops, right? So there also, which one do you think laptops will be required in hundreds, thousands, or lakhs? Lakhs or even millions, right? So in that case, which one will be more productive? ASIC or FPGA? ASIC will be more productive. So this is where, based on the number of uh, units you require, they decide either to go for ASIC or they decide either to go for FPGA. For example, you take uh, some aeroplane related hardware. You see everywhere hardware is there, right? Even in the cars, there is a hardware. Even in flights, there is hardware. Which one do you think they may prefer? They will prefer FPGA because the number of flights that gets manufactured is thousands, hardly, right? Thousands of flights are only getting manufactured. Because of that, if they go through ASIC, the bigger problem with ASIC is it is time intensive. See, the another disadvantage with ASIC is what? It takes time. mean, here it may take almost 8 months. The same thing, you may finish it in 3 months here. Same thing, you may finish it in 3 to 4 months, because you don't have to, you already have the board that is available. So you don't, the physical design will be simpler, DFT will be simpler. A lot of things will be simple because you don't have to do anything related to the hardware. Hardware is already given to you. You just need to program it the way you want it. I hope you got an idea how we arrived at 1200 here. Now, don't think that 1 lakh is always fixed. Don't think that this 10,000 is fixed. These numbers could vary, but it is a rough estimate, rough thing. Because of this, wherever the items required is less used, let's say if I take an example of a oscilloscope, do we use it in every house? No, right? Whereas mobile phone is used in every house and every person uses. So oscilloscope kind of things are only used in the laboratories, right? So what do you think would be manufactured? Probably thousands. In that case, they may again go for FPGA only. So based on the number of things they need to manufacture, they decide that I will go with ASIC flow or I will go with FPGA. So now tell me which one is better, ASIC or FPGA? ASIC. Going by the previous slide, if you see in the previous slide, going by the flexibility, we thought that FPGA is better. But going by the cost involved, ASIC is preferred. That is this graph. See, ASIC initially will be cheap, but at one point, FPGA gets more costly, ASIC is less costly. See, this is the fixed cost. This is the fixed cost of ASIC, the horizontal line. You see, 85% of the companies manufacture product for bulk usage. So they will all use ASIC. Which company go for FPGA production? 15% of the company which manufacture for limited applications. I hope you got it. So what is that you need to understand from here is two things. One is, in industry, lot of work happens in ASIC. Less work in FPGA. How much work roughly? 15 to 20% of the work into FPGA. That is where you see lot of opportunities in ASIC and lot of people undergoing training in ASIC. But coming to FPGA, then it has got its own advantage. Very few people join FPGA training. I mean, if I will tell you the statistics will be, yeah, this is what 85 is to 15, right? The number of people who undergo training in ASIC and FPGA will be probably 50 is to 1, or maybe 50 is to 2. Means for every 25 people who join VLSI training, ASIC training, only 1% or 2% joins FPGA. So which has got a better ratio in terms of the job chance? FPGA. I mean, if you see the absolute numbers, if you join a training, where do you stand better chance of getting job is a FPGA. Because company won't say, right, because people are not undergoing training in FPGA, all people are joining ASIC training, so I will go with ASIC flow. Do you think company will do that? Let's say Boeing is there, they want to manufacture electronic system for their in-flight. Okay. Do you think that they will see training institutes are all providing training in ASIC, so I will only go with ASIC flow? No, right? They will not stop, because what they will do, if they don't find the engineers, what they will do, they will hire ASIC engineer only. They will ask him to ramp up on FPGA. They will ask him to learn FPGA. But institute don't play the role. It's the companies which drives things. But then what people see is, people see a lot of places, all the openings are ASIC. So they will only think ASIC. But FPGA also the requirement. Simple things, right? Logic you can see, right? So there is, so going by that, there is always a good chance of getting a job in FPGA, purely because less competition. Just because of less competition. I'll give you a simple analogy. let's say even in our institute right now, there are 100 people who are in PD who need jobs. Okay, number of opportunities are very less as of today for PD. Okay, same thing FPJ. Even if I have 10 people, I can place all day. Just because in FPGA market there is no other, not many institutes who provide the training, and when there are less people available in the market, companies hire what they get. When it comes to domain where more people are involved, they tend to be choosy. What they will do, they will filter out based on percentage. I need only 75% because there are 100 people.
உங்க லேப்டாப் எடுத்து போடுங்க.
Then they will say recent pass outs. They will put lot of here. When there are only 10 people, their restriction, their cutoff will be very limited. They cannot put too much cutoff. If they say 75%, there will be only 2 people left. Okay, so just do think over this. Okay, why I'm telling all this is, I mean, I am not FPGA person, I'm into ASIC, so I want to give you the basic information so that you make a right decision. I mean, don't think that going into FPGA will be like doing some low class work or anything like that. It's a equally as good as ASIC work. The salary wise, the growth wise, everything is as good as ASIC. It's just the perception. Okay. Other advantage of FPGA is that you get to see the entire flow. You start from RTL, you can even see the implementation onto the board, and you can see the board also working. In ASIC you don't see that. In ASIC you only see one activity. You will only do verification, you will only do physical design, you will only do DFT. So accordingly you make a decision. Now let us talk about ASIC design flow methodology. We have talked about house construction example, right? See, requirements. What is requirements means? What kind of, you may be thinking why we are taking house construction. We will correlate it. See, on the other side, I'll take an example of a mobile phone. So even mobile phone will have a requirements, right? What kind of mobile phone do you want? What are the application? Okay, then once
கரெக்டா சாக்ஸ் போட்டா இன்னும் கொஞ்சம் டைட்டா.
Bruno, please be in mute. Bruno, please be in mute. So why are we taking an example of a house construction? It is something you see every day happening, right? You will be able to easily correlate what is what. If I, on the right hand side, if I take mobile phone example, like the way you have requirements for house, you will have requirements for a hardware also. So you collect the requirements. Once you have collected the requirements, whom do you go to? You go to the house architect, right? There will be design architects will be there. What architect will do? He will take the requirements from you. He will ask you what is your requirement. Same way here also, there will be someone called as chip architect. There will be architect. What is his role? He will take the requirements. What kind of mobile phone do you want? What kind of hardware do you want? What processor do you want? What kind of USB do you want? Everything he will ask you. Based on that, he will come up with the architecture diagram and different plans he will give you. Same way in VLSI also, what is my the chip architect will give you, he will give me the architecture diagram, he will give me different specifications, various documents he will give. Once you have gone to house architect, whom do you go to next? Mestri. Like what he will do, he will take whatever is the output from the previous stage, he will take it as an input. See, this becomes input to him, right? Then he will give you the building structure. Same way in VLSI also, there will be one team called as design team, RTL design team. What is that called as? RTL. RTL stands for Register Transfer Level Design Team. It's a team, simple. RTL design team. You go to him. What he will develop? He will develop the Verilog code, which represents the design behavior. Then you see, you go to various people, right? Plumber, electrician, carpenter, painter. Finally, what you have at the end? You have the house constructor. Same way in VLSI also, you go through various stages. You go through various stages. Okay. Okay. To get the chip manufactured. So that is something we have listed here. Please read these ones. Go through these ones. You see, in the house construction example, there were various stages involved, right? Even in ASIC, there would be almost 12 to 15 steps. That number of steps depends upon how we divide that. Same, let's say if I tell you in house construction, how many people are involved? How many stages involved? Someone may say 10 stages, someone may say 12 stages, someone may say 8 stages, right? Same way here, it could be 12, it could be 14, it could be 15, depending upon what all different activities we are doing. Majorly, these all activities are divided into two parts: front end, back end. One is the front end domain, one is the back end domain. What all activities are there in the front end domain? Design requirements, architecture, RTL coding, RTL integration, functional verification, DFT at the RTL level. So these are the stages. Almost 6 stages are there. It is, in summary, it is nothing but coding and verification. Okay, or rather I would call it as, that's why we are calling it as RTL design and verification. The front end course, why we are calling as RTL design and verification course? Because this is the stage where you do the RTL designing and where you do the verification. So that is what is essentially the front end domain. Then once this front end domain is done, what is the next domain after that? Back end domain. Now tell me logically which one should happen first, front end domain or back end domain? Front end, right? Even in the house construction, you have to go through the specific flow. You cannot first do painting, then you cannot start the construction. You have to have a specific flow. In backend domain, first it starts with something called as synthesis. What synthesis does is it converts whatever RTL we have developed, it converts it into gate level. Then we have DFT. See, DFT is done at RTL level also, is done at the gate level also. Then we do physical design, static timing analysis, custom layout, physical verification, GDS2 extraction. Now, do you remember GDS2 we talked about? So that means this is where our work ends. Once this is extracted, whom do we give GDS to? We give it to the foundry. What foundry will do? They will manufacture that on a this kind of silicon plate wafer. Then they will cut it like this. They will give you these pieces too. They will give you those pieces too. Each piece represents one chip that goes into final thing. Now there is always a chance that some chip can be good, some chip can be faulty. Like when you are manufacturing something, there's always a chance that some manufacturing defect can happen, right? To figure out which chip is good, which chip is bad, we use something called as post silicon validation. What is post silicon validation? Out of 100 chips, how many are good, how many are bad? That is figured out by a step called as post silicon validation. Why post silicon validation is important is, if you don't figure it out at the chip level, once it has gone into the mobile phone, there if you report an error, let's say I purchased a mobile phone and I see that it is not behaving properly. So will it be good for the company, let's say for MI2 or whatever, right? For this company, will it be good? No, right? What rather they will do before they put it into the mobile phone, what they will do? They will check the chip, individual chip, is it working fine? That is called as post silicon. Post silicon means what? Once the silicon has been manufactured, they will do the validation. Only if the chip is good, it will go into the final product. If it is bad, it will be thrown away. It will be thrown away. Okay. In this, let's say out of 100 chips, 92 chips are good, 8 chips are bad. So this fabrication yield is called as 92%. You will hear a term called as yield. Okay, in manufacturing. How many manufactured chips are good? That percentage is called as yield. Anyway, for you and for me, it doesn't matter, that whole thing. But you got the idea, right? Right. Now, today's session focus will be on front-end domain. So I'm not going to talk about this. Talking about front-end domain, it is very similar to software job role. It is very similar to software job role. Okay, because here also you have to do the design and you have to verification. In software, what they call as, they don't call as design and verification, they call as what? Developer and tester. So design is nothing but developer, verification is nothing but a tester. What is the language they use in software? C, C++, Java. In VLSI, we use Verilog, System Verilog. Verilog is used for a design purpose to develop the design code. To do the verification, we use SVMD. Do you see a lot of things similar between software and VLSI front end? In software, what is the skill set like for someone to get into Google, let's say, or Microsoft? What is that they learn? Tell me, software engineer, what do you learn? Does he learn C, C++ or something more important? What is more important? They learn algorithms. You might have heard there will be a lot of algorithms. They learn algorithms. More number of algorithms they know, better software engineer. Then what does he do? Learn the algorithms. He will implement the algorithms using C and C++ languages. Got it right till this point. So what does software engineer do? First, he will start off with learning the basic languages. But if he wants to grow in the career, he won't keep learning C, C++. After 10 years, person won't sit and keep doing C examples or C++ examples. What he will be doing after 10 years if he has to grow? He will learn more complex algorithms, how to implement the algorithms, how to understand algorithms. That is where he will grow in the career. In VLSI also, Similar to algorithm, there is something called as protocols. What is an example of a protocol? USB protocol, HDMI protocol, DDR protocol, SPI protocol, AMBA protocol. Uh, Similar to C, C++, Verilog. So what is that you will start off with first? Let's say when you want to start your career, what will you start with? Will you start learning protocols or will you start learning Verilog SP? You will start learning Verilog and SP. Will you be learning Verilog SP for all 10, 20 years of career? Then what will you start learning? Protocols. Similar, very similar here. Even today at whatever my experience, I'm learning new protocol. Okay. Because only if I learn protocol, I will be able to understand different domains. Let's say today I'm sitting and learning DisplayPort. What is DisplayPort? Also, I'll tell you. Simple example. How the information gets transmitted to my projector. What is the port I'm using here? HDMI. So HDMI is the port that I'm using currently. But what is the advanced version of HDMI? What is the next generation of HDMI? Can someone tell me? See, before HDMI, what was there? VGA. Then we have HDMI. Then what is the new thing that you hear now? DisplayPort, which probably you won't have in laptop, but at least after 1 year, DisplayPort will become the standard. HDMI will become the redundant. HDMI will be there just because of backward support, but all your laptops is going to have DisplayPort. Now DisplayPort, what is the DisplayPort will tell how the information goes from my laptop to projector. See, it will carry audio information also. Someone is speaking. Sometimes you can hear their audio in the projector. Are they sitting here? No, right? They're sitting somewhere else. Where is the information coming to? Is it directly going to projector or my laptop? My laptop. From my laptop, that information going to projector. So projector has a speaker, it will play out that audio. So the display port will tell how this information goes from my laptop to projector. So that concept is called as protocols. The rules that gets followed in carrying the information from one point to the other point. So I was just trying to correlate software engineer role with a VLSI front-end domain engineer. Why these all things are important for you? It is important because you have to ask yourself, am I interested in this kind of work? When learning languages like Verilog, SV, and the UVM, learning some protocols. Okay. So based on that, you should choose which is the right domain for you. Finally, after post-silicon validation packaging, once that is where you have the actual hardware. So as I told you before, front-end domain flow is similar to software flow. What is the software engineer skill set? C, C++, Java, understanding requirements, develop algorithm and implement using C, C++, Java. What is similar to front-end domain engineer? What is the skill set? Verilog, SV, and UVM. Like, what is the difference between C and C++? C++ is an object-oriented programming language. Same way when you go from Verilog to SV, SV is also object-oriented. What is the difference between C++ and Java? Are they completely different? No, right? They are similar. Java is the improvisation of the C++. How to use C++ effectively. Same thing is the relation between SQL. Next. Here you are learning algorithms. What do we learn in front-end domain? Protocols. You read the specifications, implement requirements using various protocols. USB, PCI Express, DDR, SPI, various things. Okay. In only difference. Now, what is the difference between software and VLSI? In software, there is no backend flow. But in VLSI, backend flow is there. What is meant by backend flow is You go and you want to purchase a mobile phone itself. When you go to shop, will he sell the Verilog code and tell that use it as a mobile phone? You go to a shop, you say I want to purchase a mobile phone. Will he give you Verilog code and tell that use it as a mobile phone? No, right? So that process of starting from Verilog code, the chip till the chip gets manufactured, that is called as backend. Everything till you develop the code and verify the code is working is called as front end domain. Once the code is developed and it is verified, the things you do after that, what all is involved in this synthesis, physical design, DFT, STA, custom layout, various stages are involved. They are collectively called as backend. So for VLSI to work, both front end domain and back end domain are essential. You cannot say which is important. Can we say anything is important, anything is less important? No, right? Everything is important. Both front end domain and back end domain is also important. What is back end flow? Process of converting the code into chip. Chips don't have any concept of patch. See, the major difference between software and hardware is once an electronic product is manufactured, if there is any fault in the mobile phone, you have to throw it off. You cannot do any fixes inside the hardware. Correct, right? Let's say chip has some fault inside it. Can I open the chip and fix something? No, right? It's too small to do anything at all, right? Whereas in software, is it possible? Let's say there is an application, something wrong, application is wrong. Can we fix the application? It can be fixed, right? Because you just have to fix the code, the applications will start working properly. So the software will always have a patch. See, for that matter, even in Windows, I keep getting the patches every day. Forcefully, they'll keep installing the patches, right? In hardware, there is nothing like patch. They cannot release that next hardware fix is there. You take it. They cannot give you that. Any fixes that has to come only come at the software level. So this is where comes the two aspects, front-end domain flow, back-end domain flow. What is involved in front-end domain flow? Requirements, architecture, design, integration, and functional verification. What is involved in the back-end domain flow? Synthesis. The GLS is not exactly DFT, physical design, STA, custom layout, physical verification, fabrication, and finally post-silicon validation. So going by that, we'll do for another 5 minutes and take a break. Uh, Majorly, how many domains are there? Front-end domain, back-end domain. The person who works on design requirements is called as marketing team. I mean, whoever collects the requirements. Let's say I want to come out with a mobile phone after 2 years. 2025, I want to release one mobile phone into the market. I want to sell. So first what I will do, I will keep one team called as marketing team. They will gather the requirement. They will see in 2025 what will be the requirements. Because whatever is today's requirement, 2025 will be different. Because there people will expect more bandwidth, more performance and all that. They will see 2 years down the line what will be the requirements. So then architecture, who will do? Design architect. RTL coding, RTL design engineering. RTL integration done by RTL integration engineering. Then we have functional verification done by functional verification. See, in the end, just add engineer, that's all, functional verification. Then you have DFT, you have DFT engineer. Synthesis is done by synthesis engineer. Then we have formal LEC, formal verification engineer. So like that, if I start putting DFT engineer, physical design engineer, static timing analysis engineer, layout engineer, physical verification engineer, fabrication engineer, PSV, post silicon validation engineer. Like this, these many job roles. Here in software, if you go back to software, this much confusion is not there. In software, if you want to join a training into software, you'll only ask two questions. Do I want to join for developer role or tester role, right? Simple. Because they never had this part. In software also there will be architect, you know, right? Software architect also will be there. But see, why you don't undergo training for architect? Because they don't hire people in, they don't hire the freshers for architect role. At least they need 10 to 15 years of experience to become a software architect. Then only you can, I mean, at that experience only you can become. So in software, it's very simple. Either you develop target to become a developer or you target to become a tester. So that is where VLSI gets more difficult to choose the domain. Like first you have to decide with these many domains which domain to go. So this is where we will understand. We'll take a break now. Once we meet after the break, we'll understand how do you choose the right domain. I mean whether to go into front end domain, whether to go into back end domain. Let's say you get into front end domain, which is the right subdomain for you. All those things let us discuss after the break. So we will meet by 11:15. Okay. Or 11, let's meet by 11:15 and we'll continue further.
This conference will now be recorded.
So let us resume this session. So we were discussing about VLSI domain, different job roles. We understood that majorly the job roles can be divided into two parts: front-end domain job roles, back-end domain job roles. The interesting thing here is that whatever decision you make now is something you will be, it is going to impact most of your career. For example, at one stage, let's say I decided that I will be working into functional verification. For almost 14 or 15 years of my career, I was only functional verification. I didn't do anything other than functional verification. Let's say some of my friends from my college, let's say they got into physical design. Even for them, for their 15 years of their career, they are working into physical design or related fields only. Physical design, STA kind of fields. That means whatever decision you make here, in 95%, I mean, in major chance, you will be working into only that domain unless after 3-4 years you decide that no, functional verification is not good, I want to switch something else. Okay. So hence the decision making at this stage is important for you. So how do you decide? One is of course based on the job opportunities. More importantly, based on what is your domain of interest. As I told you, front end domain is more programming oriented job. Like similar to software, you have Verilog language, system Verilog, and UVM. So if you are interested in those kind of things, you go for front end domain. Otherwise, you can choose back end domain. So I will also be talking about the job opportunities, and that will also give you one more input to make a decision. So anyway, let's talk. Currently, what I see is a lot of opportunities into functional verification, and there is a more hiring happening there. So let's again understand that from some example, some numbers. Uh, Here, let's try to understand how does an ASIC team distribution looks like. A typical ASIC team distribution. Okay. Let's take an example of a mobile phone SoC project. You go to who are all the mobile phone manufacturers are there? Qualcomm, MediaTek. So these are Samsung. Okay. If you let's say assume that one of those companies has 50 total team size. What is the total team size? 50. Out of that 50, around 25 to 30 people will be working into front end. 20 to 25 will be working into back end domain. See, relatively more people into front end domain, less people into back end domain. Out of the 25, 30 also, only one will be the architect. Around 4 to 6 will be into design team, between 15 to 20 into verification. Okay, you can see that close to 30 to 40% of the strength is into only one domain. Of all the front end engineers, Ananya Kumar, please be in mute. Asif, please be in mute. So in the front end domain, majorly people are working into functional verification. In back end domain, where do you see the major opportunities in back end domain? Physical design. Around 20 to 30% of the people, around 30 to 40%. So that means if you pick any VLSI engineer randomly, what is the chance that he is a functional verification engineer? 30 to 40% chance that he will be a functional verification. And what is the chance that he will be a physical design engineer? 20 to 30%. The 20 to 30% chance that he is going to be a physical design engineer. That is where uh, more hiring happens. Now let's understand. See, in this case, there are only few people out there. Because architect is only one, will they go with fresher or experience? Experience, and even that too very highly experienced. Even here, how many people are required? 4 to 6. So will they go with freshers or more experienced? Experience only, right? Because they have only fewer positions. It is good to have a experienced people working into design. In backend role, uh, so the point is, uh, most of the requirements in functional verification in the front-end domain are into functional verification, and lot of requirements in backend domain are into physical design, because they need more number of people. Let's say in functional verification, let's say they require 20 people in a team. They will keep some of them to be freshers because they will eventually learn and become the experienced people. Same thing for backend domain also. They will hire freshers into physical design job role, and then eventually they'll become the experienced. That is where you will see majorly fresher hiring happening into 3 4 domains. Which are the domains where fresher hiring happens? One is into functional verification, one is into physical design, partly into DFT, partly into custom layout. So these are the major domains where fresher hiring happens. Other than that, if you go to FPGA also there is a lot of fresher hiring happens. Then going to the next slide. Now I'm going to talk about the RTL design and verification training summary. See, you may hear me telling design and verification training, functional verification training, or ASIC verification training. All these domains are same. I mean, whether I call design verification training or ASIC verification, functional verification, or front-end domain training, everything is same. Okay. Next, the mode of training. Basically, training is available in full week mode, weekends only mode, and e-learning mode. So let's talk about full week mode. Full week mode again, you can attend in online, offline, or hybrid mode. Uh, what does it mean? I mean, you can attend 100% of the course online. You can also attend 100% of the course offline also at the institute premises, or you can also hybrid model, attend hybrid model. Means what? Some session you come online, some session you attend offline. That is also possible. Let's say someone is staying 20 kilometers from the institute. Dinesh, please be mute. This is the point of the question. Dinesh, please be mute. Can I tell each and every student? No, right? They have to understand. When I tell every student has to understand, they have to go into mute. So hybrid model means why hybrid model is possible is whatever session I'm doing online to the students online, and same session is being done for offline. You don't see any difference. Even students attending online also don't see any difference. The way we do the training session. Because of that, let's say today you attend offline, tomorrow you can attend online. You will not face any difference in the training. In all these cases, you get access to the recorded video for 10 days for every session. Let's say today you attended a session, for next 10 days, that session video will be available. You can also attend weekends only training. That is mostly for the people who are working. It is online, offline, or hybrid model. You get in this case, you get access to all the recorded videos uh, for entire course duration, because you are only attending. Someone is who is attending only weekends, they will they will have some times free time during the weekdays in the evenings, right? So what we do is we give access to all the recorded videos for entire course duration. And evaluation test. Okay, we will be conducting evaluation test for each topic. Now, functional verification is 32 weeks training, 6 days per week, 4 hours per day, 9:30 a.m. to 1:30 p.m. and recorded video access for 10 days for every session. And the training is divided into 3 phases. Uh, what is it called? Let's see. Those attending online, do you see any noise?
Ye-
Yes.
Who is the
Yes,
other
we
person
did.
who, from?
Yes, sir.
I mean, other than me, whom do you see the audio? I mean, this noise coming from? One second, I'll check.
Dinesh.
Dinesh, sir.
Let us see. Okay. Dinesh, please be in mute. So we were discussing about the functional verification training. It will be for 32 weeks. See, we purposefully have kept it to be so long. Most of the other places you will see the training gets over in 5 months, which is roughly 20 plus weeks. Okay. Why we kept this much is the training should be effective for everyone. There are three people involved in this. One is the students, one is the institute, one is the companies. Right? Let's say some company hires you, you don't know much of the, you don't know the things properly. Then many times, I would say, when I say many times, 90% of the times, they end up again training you. I'm not joking. I mean, a lot of people who undergo training, when they join the company, company feels that these people again don't have the basics, required fundamentals. They again train you. So there, who? So what is the problem? Everyone is at the problem. Student is also at the problem because he again has to undergo the training. Institute again has a problem. Why institute has a problem? Once the company makes a bad impression that, see, the people coming from this institute don't come with the proper fundamentals, the company doesn't hire. Again, company don't come to the institute again. What is the problem for company? After all training, again they have to spend resources on training them. So what is that we figured is the majorly the problem is to do with the duration that's being spent. Whatever 20 weeks is not really sufficient. Now it depends again what is the kind of people who join the program is what makes a difference. Let's say person is already good with Verilog, person is very good with digital design. So he can be trained in 20 weeks. The whole training can be completed in 20 weeks. Most of the students who join the course here don't come with the required fundamentals. Let's say if I randomly give you some simple example, 10 tick H345. What is this number? Hexadecimal number. I ask you to convert to octal. There is a good chance that 75% of you will not be able to do that. I gave you a number. You can do this calculation yourself also. If I give this number and ask you to convert to octal, probably 75% of you won't be able to convert it. Simple example again. If I have a 4x1 multiplexer, ask you to implement it using 2x1 multiplexer. There's a good chance that a lot of you may not be able to implement. Point is what? The input that we start with, input means the people who join the program don't have the required fundamentals to start the training properly. There it takes almost 2 to 3 months to bring them up to the required level. Okay. Whereas if a person already comes with the fundamentals, I can finish everything in 5 months itself. Because they'll be already having the subject and it's easy to train them. So that is the reason why we have to do 32 weeks of training. But then you don't have to wait for 32 weeks to get a job. Right? You don't have to wait for 7.5 months to get a job. You will get the placement supports after 5 months of training. So let me tell you how it is going to work. During these 32 weeks, we'll have 6 days of training per week, 4 hours per day, mostly in the mornings. Okay. Training is divided into 3 phases. Initially, we'll have 11 weeks in the phase 1, 12 weeks in the phase 2, 9 weeks in the phase 3. In phase 1, we are going to cover advanced digital design and Verilog. We will also cover some Linux basics and GVim text editor. Then phase 2 will cover system Verilog language and UVM, and also will cover Linux and soft skill training. And once these two are done, how many weeks is done totally? 23 weeks. So from this point onwards, placement support will start. Placement support starts after 23 weeks of training. Then comes the phase 3. Phase 3 is where we do multiple projects, like projects based on AXI protocol, AHP protocol, APP protocol, Ethernet MAC. So we keep changing this project. Like right now, during the current year, we are doing Ethernet MAC. For the next year, we may move to some other design. So idea is to keep changing the projects so that resume don't look similar. Let's say 1,000 people we train, all 1,000 resumes should not look exactly same, right? They should look different in terms of the projects they have done. Then we also cover Python scripting, SOC basics. Okay. So this is how the overall training is divided. Now at every stage there will be evaluation test. After digital design there will be evaluation test. After Verilog also there will be evaluation test. After system Verilog there will be UVM. At every stage there will be one evaluation test, and each topic will have a lot of assignments. Even if you go to digital design there will be a lot of assignments. Mostly training will be practical oriented and problem solving oriented. For all these things we will be giving you one login. We have a portal called as inskill.in. This is our own institute portal on which all the information will be present, the materials, everything. So in this, if I go to digital design, I'm not sure why it's not working now. Okay. Yes. So digital design, there will be assignments. For example, if I take combinational logic assignment, here for each topic, radix and number systems, complements, logic gates and realization, and the questions based on multiplexer based questions. So each topic there will be a lot of questions. Again, this is what I meant by the problem solving questions. Most of these questions you will get the guidance in the class itself. Like during the sessions itself, the trainer. John, please mute. Okay. So the point I was trying to show you is there will be detailed uh, assignments for each and every topic. Let's say this is this one. Let's say if I go to sequential. Similarly, there will be questions based on theoretical latches and flip-flops, questions based on the frequency division and multiplication circuits, the counters, the code conversion example. So there will be a lot of categories of questions. And for all these questions, you get the support during the session. I mean, trainer is not going to tell you, you do all these things and come. He is going to do lot of things, how to do, he's going to show you. And when you try, if you don't get it, you can always ask the trainer the questions in the next session. Similarly, for each and every topic, let's say if I go to Verilog also, there will be presentations for each topic. There will be assignments. See, again, Verilog will have close to 20 plus assignments. Each assignment is very detailed. We are not going to do that. We are not going to tell that just do half adder. The inputs will be given, how the half adder should be developed, how it should be verified. Each question will be explained in a detailed manner how to do the task. Like that, any topic you take, let's say if I take 4 synthesis, so this also will have questions in a very detailed manner on that. And other than that, this portal is where you get the notes, session notes, whatever session notes generally would have used in the previous batches. That notes will be available, and the course presentation also will be available for all the topics. So it's like one place where you get the presentations, assignments, notes, and even you will get the videos also. I told you, right? For every session, you get the video for 10 days. This portal is where you get everything. So coming to the training, I told you that as soon as you complete 23 weeks of training, that is phase one and phase two, you will start getting the placement support. Uh, Talking about this, phase one and phase two are helpful only in getting the job. When you get into the job, phase three is what is important. This project is what actually helps you do well in the job. So going by that, all three of them are equally important. So just getting job is not sufficient, right? Once you go into the job, you should be able to perform there. So for that, this project will be very useful. Talking about FPGA system design training, like some of you may be interested in FPGA system design and verification training. It will also have similar thing. It's a 26 weeks course, 6 days per week, 4 hours per day, and recorded video access. That's the same thing. Training is again divided into three phases: phase one, phase two, phase three. Phase one is common. See, whatever is the in the phase two. Those attending online, can you hear me?
Yes, yes.
Okay. Okay. So in the phase two, basically, let me leave it to the FPGA trainer to explain you these things, because those who are interested in FPGA, we will be sending the details. Can you please message me in the chat box, whoever is looking for FPGA training here? Is there anyone in the classroom who is interested in FPGA training? Okay, fine. You can connect with us after the session. Uh, so our admin will inform you the schedule. So during the training, during that session, our trainer will tell you what will be done for each week of the training. Only thing is, every session will be theoretical and practical oriented. I mean, we are not just going to teach you theory. Each session will have the practical aspects being covered. DFP also there will be a trainer who will explain. I mean, we'll have a dedicated session for DFP also. One of the things about